All right, and welcome to my transport layer video for our CCNA lessons. My name is Johnny Bandon, and I'm your CCNA instructor for this CCNA course. So this is another one of those important lessons in our section 1 going over our network fundamentals. So the transport layer, or TCP UDP, right, specifically TCP IP, can get really in depth. And again, a lot I think trainers sometimes struggle, myself included, with keeping the content to the course you're making, right? So with this CCNA course, TCP and UDP is a big subject, but you do not have to know in-depth knowledge about it just for the certification exam. But for your knowledge as a network engineer, it wouldn't feel right to me if we didn't have at least 15 to 16 slides with a lot of visuals going over what TCP and UDP is, why we need it, and why we use it. So with that being said, let's begin. So just a transport layer overview, right? The transport layer is responsible for establishing these communication sessions between client and server, two applications, and delivering that data between them. Now we know that the IP address is what we're sending to, right? That's how we locate a device on the internet or our network, right? But the transport layer is ensuring that the data between client and server, sender and receiver arrives correctly, and we actually have some checks on if that data arrived. So an application generates data that is sent from an application on a source host to an application on a destination host, really without regard for the transmission of the data. So, use the application a lot, getting this definition, right? But essentially what this is saying is when I send an email, the IP address that I'm sending to, that internet protocol, and that email data doesn't care how the data gets there or the transmission of it. That email application, IMAP, Outlook, it's not generating a communication session to make sure the data arrives correctly. So we need a transport layer protocol and a transmission control protocol to ensure transmission application data between devices. Okay, so the transport layer is also responsible for managing the reliability requirements of a conversation between client and server, sender, and receiver. So depending on the application, and when we say application, we mean, these different apps and protocols right here, they're going to have different reliability requirements. And what that means is that if you're opening up a web page, you want to make sure that you get every single bit of that web page that that web server is hosting. You don't want to miss information. So we'll need a transmission control protocol or a transport layer protocol that ensures we get every single bit of data. If we're downloading a file via FTP, we don't want to have missing bits. We want to make sure we have something reliable, okay? So the difference between the transport layer and the IP addressing or the network layer is that IP is concerned only with the structure of addressing and routing packets, but IP is not going to specify how the delivery and transportation of packets takes place, meaning it's not going to structure our data, right? It's only caring about its IP structure and making sure it has the right IP address. So transport protocols will specify how to transfer data and messages. And there's two main transmission control protocols we're going to learn about in the CCNA. That is TCP and UDP. Okay, so TCP overview. So TCP is a reliable, connection-oriented transmission protocol. So really the basic operations of the reliability for TCP is it's going to acknowledge data being received. And what we mean by that is this guy right here typing away, going to trepatech.com. My web server over here is going to acknowledge that it got sent a request or data from that client. It's also going to do numbering and tracking of data segments transmitted. So it's going to track everything coming over and say, okay, I got 10 bits here, I got 100 bits here, right? And then it's also going to have retransmission of any unacknowledged data after a certain period of time, saying, hey, I got this data, I had to drop it because it arrived kind of messed up, send it again. So in our example here, the user makes a connection to a web server. TCP ensures the session arrives in order and reliably. So while the TCP reliability functions do provide more robust communication between applications, what happens is we have a lot of additional overhead and delays because we're always doing that sequencing and that checking. So adding overhead to ensure reliability for some apps could just defeat the whole purpose of the application itself. So for services like voice and for streaming and for gaming, you don't want TCP because you just want a constant stream not interrupted, right, of packets getting sent. You don't care that data channel doesn't lose one bit of data. And this is what happens when we're talking on the phone and it's like robotic or you lose them for a second. It's because UDP is not going to just drop that traffic that you're sending to someone on the other end of that phone. It's still going to keep sending. And if something's get dropped along the way, then okay, right? It's still going to send. If we try to do a voice call over TCP, the moment one bit of traffic was dropped, your phone call would drop. So that's why we use UDP for stuff like streaming, voice, video. So again, required protocol properties for these are fast, low overhead. We don't want acknowledgments. We don't want lost data being resent. But for TCP, where we want the entire package, we want everything in that file, that web page, that email, we want it to be reliable. We want our data acknowledged. Anything lost along the way, yes, please resend it, right? And we want to make sure we deliver data in a sequence order. So more of the TCP features. So reliable delivery, right? And then same order delivery. So networks, right, can sometimes be what we call asynchronous, where they're taking different paths, right? Well, TCP still allows the data to arrive in order, even if you're taking different paths to get there. And then if we have one computer here making a bunch of different TCP connections from its one source IP, TCP is going to take over and make sure that all these different streams of data are not getting multiplexed, right? We're not sending a message and then that bit of data ends up going to our email we're sending out over here, right? So here we look at the TCP header, and I'm not going to go through every single one of these. For you guys going through our paid course, these slides are available to you. So I wanted to make sure that we had this, for download. The most important thing you need to know about really is this source port and destination port. These are going to be our actual port numbers that we're going to get into. And then, of course, our acknowledgments, right? And, of course, our control bits. These are going to be the flags that we send. So our SYN flags and our acknowledgement flags, which we're going to learn about when we go over how TCP establishes a data session. So here we go. So the TCP three-way handshake. So the transmission control protocol three-way handshake must be established before data transmission, meaning the handshake is going to use our SYN and ACK flags between client and server, sender and receiver, to verify data connection before we start sending our payloads, right? So step one, the sender or client is going to send a SYN flag initially to the server or receiver. The flag's going to be received, then that receiver sends back a SYN ACK flag. And then the client or sender is going to send back one final acknowledgement flag. And if these flags have been sent with no packet loss, we establish what we call that TCP data channel. And now we can start sending packets. Now, during the sending of these packets, we're still doing these acknowledgments, right, of data. Maybe we're doing it with flags or the actual acknowledgement field in that header. And what's going to happen is once that channel is established, this sender, and this is like a graph, right? Let's say this is 10 megabits of data, right? Let's say, and we're sending to our receiver here, our server. Let's say we have that TCP connection established, and we're getting up to where we're sending 5, 6 megabits, 8 megabits of data per second. Then all of a sudden we lose an acknowledgement at the 10 megabits part. What's going to happen is we're going to drop all the way back down to our lowest threshold and then work our way back up to sending those packets back up to a better speed, right? So this is called TCP window scaling. So TCP sometimes has transmissions that look like this when you're on an unreliable connection, right? So especially if you have like a SATCOM connection where the latency is high, or you have EMI across your wire, just really anything, right? That's how TCP functions. That if we don't receive an acknowledgement, there's pretty much data loss. And we have to reestablish that channel to see how much we can send before it happens again. Okay, to close a TCP connection, what's going to happen is we're going to send a FIN flag, and then the server is going to send back an acknowledgement saying, I got that flag. And then it's also going to send its own FIN flag, and then this client's going to receive that acknowledgement, and then it's also going to receive that FIN flag as well right after and say, okay, so we both want to finish, and it's going to send an acknowledgement back. Once the server receives it, that TCP connection is going to be terminated. All right, now let's jump into our other transmission control protocol, UDP. So this is considered a best effort transport protocol. It's lightweight, and it offers the same data segmentation where, if we're doing streaming in VoIP, UDP will make sure that your data goes this way and this way. But it doesn't have that reliability or flow control. So, there's less overhead. It just lets you send packets without any acknowledgments, right? And UDP does what TCP can't do for these services, right? Where it's just send data. So UDP is a stateless protocol, meaning neither the client nor the server has to keep track of the state of the communication session. So if reliability is required when using UDP, it must be handled by the application. So that means some application developer will have to, if they're building an app that's centered around UDP and they want some sort of acknowledgement, they're going to have to build that within the application between client and server. And one of the most important requirements for delivering live video and voice over a network is a continuous flow, right? So UDP allows a continuous flow even with dropped packets. So with UDP, you don't see this kind of TCP window scaling. You just send data, right? And of course, if there's like a major loss where you don't even have reachability, like I'm talking IP reachability, of course the flow stops as well, right? Because someone may be saying, well, how come my phone calls get dropped? Well, that's because you just lose entire internet or IP connection, right? Okay, so the UDP connection. These are some services. A UDP connection or UDP is going to be used for unicast, broadcast, and multicast connections, which if you went through our IP addressing video, you know what those are. So that's why it's also perfect for broadcast and multicast. Multicast especially because multicast is used a lot for streaming services like Netflix, Amazon Prime, right? So we use UDP. Then here's some examples of some UDP services. DNS, I believe, actually can be both, but out of the box. Okay, so then the transport layer must also be able to separate and manage multiple communications with different transport requirement needs, right? What we mean by that is essentially when our computer is making multiple connections, we're relying on TCP or a transmission control protocol, UDP or TCP, to manage multiple simultaneous conversations, right? By using the header fields to uniquely identify these applications. So essentially, right now, we're making 3 TCP connections. Now, how do we know how to segment the bits into their own TCP data streams without mixing them up? Because we have our source and destination ports. So we know bits or data that are destined or using Outlook or email, we're going to put a header in our header, the 110 port in our TCP header. And now we know, okay, all this data needs to go this way using this destination port. And same logic for the web, 443, and for our chat applications. So that's where we have port numbers come into play. Port numbers allow us to sequence and identify where traffic's supposed to be going and for what applications. So again, here we see, just another example where we're using port numbers for our destination traffic, right? These applications have their own port numbers that we're going to assign as a destination. And then the source port number is going to be something that's generated from our client device so that once the server needs to talk back to the client, it knows where to send it as well. Okay. So each separate HTTP conversation, or really, we could change this out with TCP/UDP conversation, is going to be tracked based on source ports, right? So if I have Internet Edge tab open going to YouTube and a Google Chrome tab up going to a blog post, my source port is going to be different for each one of those streams, right? Okay, here's the port number groups. So our well-known ports are 0 through 1023. These are port numbers that are reserved for specific services and applications, kind of like we saw here, right? Well, at least for email and this web page. I have 443 here and 80. Doesn't really matter, web services, 443 secure, 80 is unsecure. And then we have registered ports. So these ports are numbers that are assigned to our Internet Numbers Association that does the registering to a requesting entity to use with specific processes or applications. So this is kind of like if I'm developing an app like WhatsApp, I can go to IANA and say, hey, I want this port to be for my application, and they can assign that to you. And then we have the dynamic or private ports. They're known as ephemeral ports. What this means is they're created dynamically by our client and our operating system when a connection to a certain service is initiated. So these are usually our source ports when we're the client, right? From the client perspective. Okay, and then we have just some common TCP applications here. So HTTP, FTP, SNMTP, and Telnet all need to have a reliable connection. Then some common UDP applications. DHCP, VoIP, TFTP, the Trivial File Transfer Protocol, SNMP, which we're going to learn about. Okay, awesome. So I want to thank everyone for viewing this video, and stay tuned because I believe in our next videos, we're finally going to get into some CLI. So stay tuned.